In 1967, a 68-year-old man rode a 47-year-old motorcycle across the Bonneville Salt Flats at 184 miles an hour on cylinders made from old gas pipe, connecting rods carved from a tractor axle, and pistons he cast in a tin can with a blowtorch. By every rule of engineering, that bike should never have worked. Here's why it did. When Burt Munro bought the 1920 Indian Scout, it was a 600 cubic centimeter flathead designed to top out around 55 miles per hour. From 1926 onward, the New Zealand rider spent decades modifying the machine, aiming for the under 1,000 cubic centimeter streamlined class. By August 1967, Munro was 68 years old, and his motorcycle was 47. To secure an official land speed record on the Bonneville Salt Flats, rules demanded two timed runs in opposite directions, taking the average rather than a single peak. That official average stood for decades until his son, John, spotted a calculation error in the logs. The corrected official average was 184.09 miles per hour, though Munro achieved a separate one-way pass of 190.07 miles per hour. The self-taught developer had constructed a streamliner that defied the limits of its original design. His performance was an outlier, surpassing factory-backed teams with massive budgets. By every rule of engineering, this bike should never have worked. To understand why the engine held together, look at the cylinder barrels. Standard racing cylinders are cast from high-grade alloys designed to shed heat and maintain a perfectly round bore under extreme pressure. Munro replaced his original barrels with pieces of heavy-walled cast-iron gas pipe, salvaged from municipal mains where they had been buried for decades. A cylinder does not care about its pedigree, it only cares about physical limits. The cast-iron utility pipe, with walls roughly half an inch thick, possessed the basic tensile strength required to survive combustion. That immense wall thickness provided necessary structural support and acted as a thermal mass, absorbing heat during short, high-speed runs. This heavy mass added significant weight and compromised overall cooling, a major trade-off as Munro repeatedly bored and sleeved the cylinders to push the displacement toward 950 cubic centimeters. The real difficulty was internal geometry. If a cylinder bore is out of round by even a fraction of a millimeter, combustion gases leak, rings fail to seal, and the piston seizes. Using a basic lathe in his shed, Munro painstakingly bored, lined, and honed the rough pipe. It required endless cycles of manual fitting, measuring, and testing to achieve a proper surface finish. The salvaged utility pipe only worked because of his obsessive, repetitive machining. As Munro pushed the engine past 6,000 RPM, the factory connecting rods began to snap under the stress. A connecting rod lives in a brutal environment, constantly pulled, compressed, bent, and violently reversed thousands of times every minute. To withstand these immense fatigue loads, Munro scavenged for stronger steel. Accounts differ on whether the donor material came from a Caterpillar tractor or a Ford truck axle, but the objective was identical: securing high-strength alloy stock. Using his basic lathe, Munro machined the axle steel into new rods, hardening them in his shed with a simple heat and quench process. While the axle steel provided massive tensile strength, it also introduced a dangerous trade-off: weight. Heavy reciprocating parts create severe vibration and rapid bearing wear, meaning strength alone could destroy the engine. Munro had to manage rod weight, balance, alignment with the piston pin, and microscopic bearing clearances. Axle steel offered no magic shortcuts. It was simply a stronger raw material that required endless cycles of trial, modification, and test runs to find the narrow margin where the engine would run fast without shaking itself to pieces. He filed and balanced the rods by hand, using a crude setup of weights and measurements to balance the reciprocating forces, knowing a single gram of error would tear the crankcase apart at high speed. With the rods sorted, Munro turned to the pistons. A piston is a brutal, reciprocating mass problem. It must survive intense heat and combustion pressure while remaining light enough to reverse direction 6,000 times a minute. Munro cast his own pistons using a kerosene blowtorch and empty tin cans. While accounts differ on the exact mold details, he primarily melted down scrap aluminum-based material, sometimes adding a little copper for hardness. These castings emerged as rough, pitted blanks. Turning them into functioning parts required hours of hand machining, filing the crowns, shaping the skirts, and cutting the ring grooves. The real difficulty was managing thermal expansion. Aluminum expands rapidly under heat, meaning a margin of just a few thousandths of an inch separated proper lubrication from catastrophic engine seizure. If the clearance was too tight, the metal swelled and locked. If too loose, combustion pressure blew past the rings. A short, high-speed run at Bonneville limited continuous heat buildup, but it never made this solution safe. A cooling error during casting or a minor filing mistake would crack the metal. Munro controlled this risk through endless fitting, measuring, and testing, proving that precision in clearance could overcome the chemical limitations of recycled metal. To achieve these clearances, Munro worked in a cinderblock shed using tools that belonged to a previous era. His primary machine was a 1930s hand-cranked lathe. He had a bench drill press, a hand grinder, and files. There were no CNC machines, no precision surface grinders, and no heat treatment furnaces. This lack of tooling created a severe engineering constraint. In modern manufacturing, precision means repeatability, the ability to make the exact same part twice. Without proper tooling, Munro had no way to guarantee consistency. Instead of relying on machinery to hit a dimension, he worked by constant measurement and trial. He would assemble the engine, check the clearance, take it apart, file or hone the metal by hand, and put it back together. He repeated this cycle dozens of times for a single component. It was a slow, physical process of adjustment. Every part became a custom fit, hand-worked, until he judged it good enough to survive a single land-speed run. Munro emptied his personal savings to fund the Indian's development. He financed the decades of engine modifications through odd jobs and occasional shifts as a motorcycle salesman. But the true financial burden wasn't just the raw metal, it was the compounding logistics of international racing. Shipping a home-built streamliner from New Zealand to the Utah salt flats required trans-Pacific transport, lodging, fuel, and official entry fees. While local sponsors and friends occasionally helped with travel expenses or supplies, every mechanical modification remained Munro's solitary work. Salvaged scrap metal bypassed the cost of commercial parts, but it demanded an immense toll in physical labor and manual fitting. Scarcity narrowed his material choices, limited his testing opportunities, and prevented any formal prototyping. For a factory-backed racing team, a shattered piston or a warped cylinder sleeve was a minor setback, easily resolved by ordering a replacement from a catalog. For Munro, a broken component meant starting over with a kerosene blowtorch and a pile of scrap. This economic reality turned his build into a chain of physical compromises, where time and labor had to substitute for capital. Burt Munro's understanding of mechanics did not begin in a lecture hall. He left school at 14 to start a carpentry apprenticeship, later working on the construction of the Ora Tunnel through the Southern Alps. He never attended engineering school. His technical knowledge came from hands-on work, careful observation, experiments, and advice from other riders. Through a practical working life, he learned to understand measurement and material behavior. For Munro, learning was a straightforward process: alter a single variable, test the change, and observe the physical consequences. It was a highly disciplined form of empirical testing. His lack of formal credentials did not make the work irrational. In the early 1950s, Munro built a modest cinder-block shed on a small plot of land in Invercargill. This single-car garage functioned as a complete, self-contained working system where the boundary between daily life and mechanical engineering dissolved. He slept, ate, and lived inside the same footprint where he built his engines. A professional factory racing program relies on distinct divisions of labor, separating the design office, the machine shop, the testing department, and the rebuild crew. Munro's shed compressed all of these functions into a single continuous loop. The practical advantage of this space came from absolute proximity and available time, rather than any magical ingenuity. He could step out of bed at midnight and immediately begin a teardown or reassembly. In this environment, the work and daily routine became inseparable, making the project difficult to contain. When a single machine takes over a life, it demands space that would otherwise belong to other people. In 1927, Burt Munro married Florence Martin. Together, they had 4 children and spent 20 years building a family in Invercargill. But as the modifications to the Indian Scout expanded, the time and attention required to sustain a household contracted. By 1947, the marriage ended in divorce. There was no malice in this separation, only the quiet friction of a project that left no room for anything else. Following the divorce, Munro walked away from regular employment to work on the bike full-time.
He built the cinderblock shed in the early 1950s, stepping out of a shared domestic routine and into a solitary existence. For the next 25 years, his world shrank to the physical dimensions of that garage. He slept on a cot next to the workbench, cooked simple meals on a small gas burner, and lived on a modest allowance from his children alongside occasional odd jobs. Normal life, with its comfort, stability, and quiet rhythm of retirement, was replaced by the single-minded focus of manual machining. He chose a narrow, quiet isolation, spending cold Southland winters filing metal and breathing cast-iron dust. It was a deliberate trade, an exchange of ordinary human connection for the uninterrupted pursuit of speed. Popular accounts of Burt Munro's career repeat a singular statistic: more than 250 engine failures. While no surviving logbook confirms this exact total, the pattern of physical destruction is undeniable. In his shed, the engine did not yield written telemetry, it delivered fragments of metal. Each shattered component served as diagnostic evidence. A seized big-end bearing was a lesson in lubrication flow and bearing clearance. A snapped rod spoke of structural fatigue, imbalance, and reciprocating load. A cracked or burnt piston revealed the exact boundaries of heat dissipation and fuel mixture distribution. These failures followed a clear chronological progression as the engine was forced to perform far beyond its original design. In the 1940s, rod and bearing failures dominated as Munro first increased the engine's displacement. By the mid-1950s, the weakness shifted to the pistons, which cracked and melted under higher thermal loads. By 1962, valve train failures signaled that the pushrod system had reached its mechanical revolution limit. Rebuilding was a constant, repetitive cycle that immediately followed testing. Munro did not treat these catastrophes as defeats, but as raw data. He was a practical diagnostician, using metal fatigue to map the physical boundaries of his machine. With each failure, he adjusted clearances, refined the fit, and pushed the Indian back to the edge, modifying the engine continuously as its speed demands increased. The destruction was simply the price of information, a brutal but effective feedback loop. This loop functioned as a disciplined, systematic procedure: observe, alter, test, break, repeat. It was not a symptom of blind stubbornness, but a method of technical measurement. After every breakdown, Munro returned to his bench, disassembled the casing, and measured the damage. He was not looking for a single, sudden masterstroke. He wanted to extract one usable next step from the ruined metal. Double-checking his clearances and tolerances allowed him to turn wreckage into progress. Persistence alone did not solve the engineering problems, it merely kept the cycle moving. The actual work was precise diagnosis. Every mechanical change Munro made to resolve one weakness threatened to create another elsewhere in the system. The machine survived only because it was kept within an incredibly narrow practical margin, where improvisation remained strictly answerable to the physical laws of combustion, strength, fit, balance, lubrication, and heat. The engine did not run on sheer willpower. It ran because Munro used each failure to align his handiwork with those unyielding physical demands. In 1971, a New Zealand Broadcasting Corporation documentary captured Munro in his workshop, taking its title from a handwritten note on his shelf: "Offerings to the God of Speed." The phrase served as an understated index of everything consumed by his obsession: the shattered metal lining the walls, the years of physical wear, depleted savings, and personal distance. In September 1977, following a stroke, Munro sold the Indian Scout to Norman and Neville Hayes for $1,300, stipulating that the machine must remain in Southland. The Hayes family still houses the motorcycle in the Burt Munro Legacy Collection in Invercargill. They preserve it in its original, hand-filed state, the quiet, material remains of a life traded for a run on the salt. Today, Munro's scarred Indian sits quietly in Invercargill. In our era of automated precision, this machine remains a silent, hand-filed challenge to the limits of human ingenuity. It proves that failure is never a dead end. It is simply data for those willing to pay the price. The trade he made was absolute, but the record still stands. What do you think of Munro's sacrifice? Share your thoughts below.